Okay, I see the recording has started, so that's
Yeah,
good.
I
And
started recording. Thank you.
okay, thank you. And then second thing, can you unmute the co-presenters if they're not unmuted already? All right. Well, with that, I will get going. Like we said, we're going to talk about storm transposition and HEC-HMS today. This is an exciting new feature, so we have a lot of content, great content to share with you today. All right, so if you've been around HMS for a while, you know that storm transposition isn't new. It's actually been in the HMR 52 storm for a long time in HMS now. What we're doing now is we're actually allowing you to transpose storms with the gridded precip method. And that just opens up a whole bunch of opportunities far and beyond what we were able to realize with transposing an HMR 52 storm. Because now we're able to actually transpose a gridded historical storm. So things that we can do with that type of analysis. First, performing a what-if analysis for an observed storm. So if you had some storm that happened near your basin, now you can just move it right over a damage center or in a location in your basin that would maximize the peak flow in that damage center. So that's a very interesting analysis to perform. We can extend effective record length for observed storms, much like you do with flow. Now you can actually move storms around to extend your effective record length. And finally, this is extremely impactful for modernizing design storm applications. There's a lot of assumptions, both spatial and temporally, that go into our traditional hypothetical storm analyses. And this kind of opens the door to start using actual historical data to drive these hypothetical storm, design analyses. So Greg's going to talk more about that in the SST section of this presentation. Here's the outline. I'm going to introduce the topic, show you some of the basic mechanics in HMS. Lauren Coe is going to go over the optimization piece. Greg's going to talk about uncertainty analyses in SST, those applications. And then finally, Josh and Matt from Fort Worth are going to go over an example application where they actually applied these concepts in a study in the Fort Worth district. All right, we're going to start with grid data. This is where everything begins with this new transposition framework in HMS. This is the grid data editor panel. We see things that you're probably used to seeing there before. What's the data source? It's DSS. What's the file name? You see a path to a DSS file. What's the DSS path name? There it is. What's new is this parameterization for storm center X and Y. And in addition to that, there's also this nice calculator button where you can calculate the grid cell of maximum precipitation accumulation for a gridded set, like a gridded precipitation record. So two things there that are new. Those are obviously optional because they don't include that asterisk, but if you want to do transpositions in HMS, you're going to want to parameterize the storm center X and Y. We tend to think of those as the grid cell of maximum accumulation. You can put them wherever you want. It doesn't really matter. That's just going to serve as the origin for the transposition. You will see what I mean when I jump over to the meteorologic model. So once again, this is the gridded data editor panel and what we've added there. So you just get to define the storm center X and Y for the gridded precipitation record. All right, jumping over to the MET model, this is the gridded precipitation editor panel. And here you're now able to specify X and Y coordinates for the transposition. So you can see I've parameterized an X coordinate and a Y coordinate. And based on what I parameterize, this is where we're going to move that grid data origin to.
So private modelers. Yeah.
All right, getting a little feedback out there. So if you're not on mute, please mute yourselves. Thank you. All right, here's an example. This is very simple math. I'm not going to verbalize the math because I know you can all do simple addition and subtraction. This is just calculating the difference between where we defined our grid origin and where we want to move it in the map model. I'll demonstrate all of that now. All right, I have HMS open. So if any of the screen resolution is small for you, go ahead and use that zoom in feature in WebEx to zoom in on what I'm displaying. I'm starting in the grid data editor panel. And like I showed before, we have these calculate buttons. So what I can do, I can just click that calculate button. And like I said, it's going to compute the location of the highest accumulated precipitation volume for the gridded set. So I just did that for X. Now I'm going to do that for Y. It's pretty nifty. You can do it automatically. If I wanted to go in and change those numbers, I certainly can. I'm going to leave it as is. Now what I'm going to do is jump over to the gridded precipitation method in the meteorologic model. And here I've already parameterized where I want to shift this storm to. This is a shift of 20,000 meters
That
to the
technology,
left in the X direction and 20,000 meters to the north in the Y direction. It's the same math that I had on that previous slide. And what I'll do is go ahead and compute that. HMS is going to shift the gridded precipitation and compute the simulation, and then we get output for the computed shift here. So you can see, just like I said, negative 20,000 meters to the left, positive 20,000 meters to the north or north direction. And we've run our simulation with shifted precip. So before I leave, I will just mention there is also an option to bias the precip based on any sort of observed bias correction grid that's out there. You could use NOAA Atlas 14, that's a common one. There's others out there, but that would just bias the precip in place, or scale it down in place and then scale it back up where you move the precip to. So that's a handy option for doing spatial corrections of precip based on observed data. All right, that's the demo in HMS. I'm going to jump back over to the slides. And this is the example I just showed. Here you can see where the storm origin was originally. This is where we've transposed the origin to of the gridded record. And then these graphics above, this is actually from our spatial results feature in HEC-HMS. These have the same scale. So you can see my scale down here, and you can just notice that by transposing that storm a little bit closer to our basin, the magnitude of precipitation has greatly increased. And so that's the transposition. Now, this is just an FYI because, I don't know, I think it's cool. There's some computational efficiency that's built into this. So conceptually, what you're doing is you're moving that transposition relative to the basin. Under the hood, what HMS is doing is it's actually shifting the subbasins underneath that grid of precipitation record. And that allows us to compute the location, the intersection indices between the grid cells in the MET model and the grid cells on the basin. We just do that computation once up front at the beginning of the compute, and then we run the entire simulation. So we're not actually transposing sets of grids. We're actually moving the basin. You don't really need to know that for your purposes because conceptually you're doing exactly what you think you're doing. You're moving storms over the basin. And then this is just another graphic of that same concept. What you input is to move the set of grids over the basin. What HMS is actually doing under the hood is moving the basins under the precip. The result is the same in either case, but it just makes for a faster compute of the transposed storm. So with that, I'm going to pass it over to Lauren to present on optimization.
Okay. Just going to share my screen here. Okay, so I am going to, talk about the gridded storm optimization now. And so this is really kind of picking up right where Tom left off, taking the transposition just a step further. So as Tom showed, we had our initial calculated storm center, and we then we shifted that to a new transposed storm center. And so if we assume our goal is perhaps maximizing peak flows at a USGS stream gauge, that transposition, and you saw with how much more cumulative precipitation was there, that actually increased our peak flow at this downstream gauge by almost 2000 CFS. So that's good. If our goal was maximizing peak flows, we're moving in the right direction. The question becomes, that was an arbitrary location that we selected. We moved it closer, kind of thinking, okay, that should increase it, but there's an infinite number of possibilities, like any of these gray dots, anywhere else, within this map extent. could any of these other locations possibly yield an even higher peak flow at our stream gauge if our goal is maximizing the peak flow there? And so that's where the optimization tools in HMS come into play. So the user can automate that storm center transposition workflow within an optimization trial. So your goal might be maximizing peak flow at a gauge, or maximizing your reservoir pool elevation, whatever it might be. You can do these things within that optimization trial. One thing I just did want to highlight is your optimal location based on your goal. It might not necessarily be within your watershed bounds. So it's important to be thoughtful about your search bounds and where you bound, where you're going to allow your storm center to fall. And then just wanted to highlight that this and Tom's example, as he had on his slide, are documented in a tutorial and guide on the HMS tutorial and guide page that kind of walk you through these, actually the exact same example that we're showing here. Okay, so we can hop over to HMS now and look at a demo. Okay, so here we've got our optimization trial, and I already have it set up mostly. This you're kind of all comfortable with. It's like setting up any other simulation run you might do. You have your basin model selected, as well as your your control specs. One thing I did want to point out here is that for your selection of your meteorologic model, when you're going through a storm center optimization where you're going to be moving the storm center around, you want to make sure that the meteorologic model that you select has transposition enabled. If it's not enabled, when you run the optimization trial, it's just going to spit back out your observed storm center because you've kind of said transposition is not allowed. So just something to point out. I don't know. I made that mistake a few times when I was first working with this. Okay, so now on our search objectives. So here's where you're kind of putting in the criteria for your search and for your optimization. So I'm using just a simplex method, and then kind of the defaults, which max 100 iterations, 0.01 absolute tolerance criterion. So for something like flow or elevation where the values are sufficiently large, an absolute criteria of 0.01 is going to be plenty. You might not even care if it's varying by 1 or 10 CFS. So that should be fine. And just a note about your search method here. I'm using simplex. I kind of know the bounds of my gridded data already and where the storm center is likely to fall, I guess, the optimal storm center, because I've run it a few times with different methods. But I did want to note that if you're looking at a much larger area, that the differential evolution method is probably more appropriate, and there is some documentation on that as well to kind of guide you through that. Yeah, so we're gonna go with this for the purposes of this demo. And then on our objective tab, so this is where you would select your your goal. Like we said, we're looking to maximize the peak flow at our Honing Creek gauge. And so our statistic is the peak discharge. And so then we would add our parameters. So when we're looking at gridded precipitation, our parameters are the X coordinate as one parameter and the Y coordinate of the and the y coordinate of the storm center as our second parameter. So of course you would add parameters here by right clicking. These are already added for us. Your element is your precipitation parameters. One thing I wanted to point out is when you select precipitation parameters, it's already loaded in now, but when you first come in and create your coordinate, create your parameter and select, say, X coordinate, it's going to automatically pull in that initial value. So that's the initial value that is in your meter logic model that Tom has already set up. So you don't have to copy that in. It's going to automatically pull that from the initial, from your meter logic model. So let me just retype in my search bounds. And then you have something, something very similar for your y coordinate, and then you should be ready to run. This shouldn't take too long. But one thing I wanted to just kind of show, and Tom already showed this as well, you can see how your storm coordinates are shifting with each iteration here in your log. I think this typically, it should be about 30 iterations or so. Okay, so got 30 iterations, and then just to show you here, that's a.
Is it able to change both parameter 1 and parameter 2 in each optimization, or does it run one with the first parameter, then run a second simulation with the next parameter?
I believe it's changing both, but that also might.
It's sampling both simultaneously. So each X and Y will change with each iteration.
Mm-hmm. And just, yeah, so that finished up was about 30 seconds, 36 seconds to finish that. So we'll hop back over to results. Here you can take a look at your objective function summary on the maximum peak flow, as well as some other graphs that we'll hop back over to the PowerPoint to take a look at. So this is just going over, just so it's documented in the slides, some of the things I talked about during that demo. Okay, so now we can take a look at results. If we look at this first plot here is showing the evaluations. So you can see that this was 70 evaluations in total. And you can just kind of see its initial value, of course, is starting at the 10,400. That's where we started off because we started with Tom's transpose coordinates. And then by the end, we've got a really nice straight line here where it's varying very little. And now we've homed in on our optimized location and optimized flow rate. And then very similar, of course, image than that Tom showed. So we have our calculated versus our optimized storm center. Again, the magnitude of precipitation, the cumulative precipitation is much greater. And now if we look at our calculated, where we started, or our observed data really, our transposed got us here. And then our optimized location, we moved a little bit further away from the subbasins, but we got an additional 1,000 CFS. So from 8,600 to 11,300 CFS through that optimization, we're up around 2,700, almost 3,000 CFS from our observed data. Yeah, so you can see that it might not always be intuitive, but that's kind of the optimization of a gridded storm in a nutshell in HMS. So that's all I have. So now I think I'll turn it over to Greg for some talk about uncertainty analysis and SST applications.
All right, great. Thank you, Lauren. I'm going to steal this away. We've had some good questions roll in. Please keep sending your questions in the chat as they come up so we can make sure that we've got several members of the HMS team on so that we can try to respond to those as quickly as we can. So I'm going to talk a little bit about stochastic storm transposition. A lot of this is under the guise of the work that we're doing to support the FEMA Future of Flood Risk Data program. I've given several different flavors of this talk to different audiences, and this is by far the most abbreviated version of it. So if some of this is very interesting to you, please reach out. I have a lot of other material on this that we can talk about. So with all apologies to Dave Rosa from FEMA, who's on the call, this is going to be an extremely brief overview of FFRD, but the Corps is doing a lot of work right now to support FEMA in its efforts to modernize its characterization and communication of flood risk throughout the country. And one of the biggest efforts in there that we're involved in is one of the primary objectives of this study, and that's to shift from binary to graduated risk analysis. And so for anybody who's worked with a flood insurance rate map before, you've probably been aware of the fact that floodplains are delineated generally as solid regions with hard lines on the boundaries. And the purposes of these maps, they're regulatory, there are non-regulatory purposes, but in general, it's for making a yes-no classification of a structure, whether or not it's in the regulatory floodplain or not. And so generally, we draw these maps with a boundary for the 1% AEP floodplain and the 0.2% AEP floodplain boundaries on there, as well as the regulatory floodway. These are used for making a decision about generally mandatory purchase of flood insurance for a structure for the National Flood Insurance Program. But the trick here is this does a very poor job of communicating the actual risk for a structure in the floodplain. For example, any structure that is closer to the river than where the line for the 1% AEP floodplain is drawn generally has a higher flood risk than structures drawn further away. And so one of the questions we generally have is how do you adequately communicate the risk that's truly posed to a structure? And so one of the concepts that we're working towards is a more graduated definition and illustration of flood risk in an area. This is an example of annual exceedance probability grids, which give you for any of the pixels in the map an estimate of the annual exceedance probability for flooding in that location. And in order to do this, we have to pretty thoroughly modernize exactly how we're applying all of our meteorological boundary conditions for these types of analyses. The way that it's currently done, and for anybody who's done these kinds of studies before, whether it's FIS studies or a lot of planning studies, we start with a fundamental assumption that we're going to run a storm event whose probability is the same as the flow event that we're interested in. So for example, if you want to run if you want to get a 1% flow, you have to run a 1% storm. And that's a really important assumption for that kind of modeling. We get that information from depth, duration, frequency curves. So generally today we use NOAA's Atlas 14 for that. That gives us the relationship between depth, frequency, and duration. So for example, the 1% AEP 24-hour precipitation gives us a depth. That information comes from a large regional analysis of precipitation. But in order to put that into our hydrology model and turn that into flow, we have to make a large number of other assumptions in order to actually do the modeling. One of the most crucial ones are the characteristics of the design storm. That involves how do you split up that total depth in time? How do you split it up in space? How do you account for area reduction when what you're interested in is a watershed average precipitation frequency curve? And so those are all assumptions that require a whole bunch of other inputs to this that require you to make assumptions about what's reasonable. The same goes for developing a hydrology model, because the parameters that you get for that model, it's calibrated to historical events. There's uncertainty in the true values of those parameters. And so you have to make assumptions about which ones you're going to pick. And then another very important consideration is the initial conditions. So when you run that design storm event through your hydrology model, you have to make accounting for all of the initial conditions that go into the model in order to get the right flow frequency curve out the backside. And so when you go about an exercise like this, there's a large number of assumptions that go into the process. And so what we're proposing to do as part of this FFRD effort is move towards a data-driven approach for doing design storm modeling that relies far less on these types of assumptions that we've been doing in the traditional modeling paradigm in the past. The approach for SST, stochastic storm transposition, I gave it kind of a flavor phrase. I call it non-parametric space for time substitution, because the way that the entire process works is for a watershed of interest, you look at a large homogeneous region of meteorology around it. So you look to areas that include that watershed that you'd think that the meteorology is all the same in that area. And what you do is you go through the historical record, usually using, in this case, gridded precipitation data, largely radar-derived products, and you look at the largest storm events that have occurred in that very large region. And you generally don't just take the largest storm event of the year. You're taking the top 5, top 10 events per year. And what you're doing is you're building a large catalog. And the goal here, when you do this stochastic storm transposition work, is to take the largest storm events from this region and move them at random throughout the or not the watershed, but the entire transposition domain. Now, the way that this is done preserves the properties of those real storms. We don't do anything to idealize those patterns. We don't reduce them to time curves. We don't have to apply area reduction functions. We don't have to decide how precipitation is split up among the subbasins. We take those grids and transpose them just as we have here in the optimization routines and in those deterministic transpositions that we showed before. Now, using a large catalog like this gives us that space for time substitution that expands our record length in a similar way that we base our precipitation frequency estimates on through regional analyses. So by doing this, we gain the benefit of having more explicit consideration for space-time patterns of these storms and don't have to do things like apply area reduction, which is a very sensitive assumption. And we still build off a very large catalog of severe events that allows us to have confidence in our estimates. There's also a very big upside to doing a method like this is that we transpose multiple storms per year. So we don't make any assumption that a storm is the annual maximum storm. What we do when we transpose these events over our watershed is we extract from key areas within the watershed. For example, if there's multiple damage areas in a watershed, we extract the annual maximum series of the resulting flows, acknowledging that one storm isn't always going to be the annual maximum everywhere within a watershed. So by transposing multiple per year, we're allowed to capture that variability in space-time patterns when we do that. And this is a little more of a graphical way of illustrating how this whole thing happens. But in our target watershed shown here in gray, we've drawn a transposition domain, which is the dashed box around it. This is highly idealized. And say, just as an example, we had an observed storm, which in this case here is shown with the blue iso-Hyets. That's, say, I don't know, 4 time step, maybe that's the half-inch iso-Hyet. And this shows 4 time steps of a single storm event. And what the transposition process does is it takes that storm and moves it to another location within the transposition domain at random. The transposition itself is done uniformly in both X and Y. So basically, it can occur at any location within this transposition domain with equal probability. And then this process is repeated a very large number of times. So there's 2 components. There's a selection of storm. Each time we do this, we select a different storm with equal probability from our catalog. And then we move it at random to any point within this watershed with equal probability. And you repeat this process a very large number of times. So I've mentioned the big upside to this is that we capture that natural variability of spatial and temporal information that's contained in those historical storms. And here's an example of one from the USAE storm catalog, but these storm patterns are extremely dynamic. There's localized pockets of very intense rainfall that occur. Widespread rainfall in some events can occur over very large areas at very high intensity, and in others it's very intensely localized. And accounting for that variability through very highly idealized design patterns is very, very challenging. And so by using these storm events as they occurred and transposing them, we're allowed to avoid some of those assumptions, and especially crucial ones like point to area. Now, the big assumption that we're really happy to be breaking free of is that we don't have to make the assumption that the frequency of the precipitation doesn't necessarily equal the frequency of the flow. And what that means is that it's not always one event causing the annual maxima at all locations in your watershed. You're allowed to have some of these localized pockets potentially creating intense localized rainfall that for small drainages is a very rare event. Meanwhile, the entire event over your watershed is not nearly as rare. So that shakes out in that whole analysis. And then there's 2 things we can do. We could take this and run our hydrologic model with it and get our flow frequency curves directly, or we can use this process without running any hydrology at all and derive basin average precipitation frequency curves, which again gets us outside of some of the point to area reduction. So to do this in HMS, sort of kind of a complement to the optimization trials, the uncertainty analysis in HMS. It looks and feels very similar to it, but instead of having an automated procedure that searches for the best parameters, what this does is allows you to provide a structured means for sampling them. You can systematically vary, in this case, the X and Y parameters, and then for your hydrologic model as well, you can do variation of those hydrologic parameters. In this case, I'm showing basically the definition for the X coordinate using a uniform distribution. So this means that anywhere between these coordinates is equally probable for that storm to occur. And for application of SST, that's generally what you want to do. Now in HMS, there is an option. So instead of using simple distribution, you can use something called the specified values option. And so you can actually give it targeted coordinates that it can run through. So if you have a particular scheme for the sampling that makes sense for doing this that you want to apply, you can have it follow those coordinates, and it'll iterate through that list of coordinates in a manual way, which gives it control if that's specifically what you seek. Some of the enhancements to fully build out the SST process in the future. One of the things right now that we're working on is randomly selecting the storm events. So right now you could take a fixed event, one known event. For example, here in the uncertainty analysis tree, you can see I've got an event from a number of years. You take that fixed event and you transpose it at random. And one of the things that we're working on is allowing for the parameter to be selected as the storm itself. And so what that'll do is the combination of those two things, it will let you do full SST by randomly selecting a storm and then randomly transposing it and then doing it a very large number of times. So this is just an example of the results of transposing a pretty large event that happened. This is for a little watershed in east central Iowa. It's about 100 square miles over here. And this is an observed storm event that happened absolutely nowhere near that watershed. And we determined that this boundary here around the state of Iowa is reasonably homogeneous for the purposes of transposition. And so what we did is we took this storm event and transposed it 2,000 times. And so this little center of the storm, you can see in the black outline right here, was moved to 2,000 positions within the domain. And in the plot at the right, you can see the results of those transpositions where red resulted in the highest peak discharge at the outlet of the watershed, and then it kind of descends through this light red to white to gray to dark gray. Now, there were more transpositions that are not shown. Those were all transpositions that resulted in a peak discharge that was less than the 2-year flow at the outlet determined by USGS stream stats. So what this does is this gives you an idea of how sensitive the runoff is in this watershed to the spatial and temporal pattern contained within this storm event by moving it around a large area. So there's a lot more to come on our development for SST to continue to support the FEMA FFRD effort, but we have the fundamentals in place right now to be able to show this off. So that's what I've got, and we're going to keep this train rolling. So Josh, go ahead and take it away.
All right, thanks, Greg. Give me just a second here to share my screen. All right, so we've kind of been bouncing around a little bit. So just as a quick recap, Tom and Lauren both demoed some of the new storm shifting and storm optimization tools in HMS. Greg talked about how those tools are building the foundation for SST analysis, and that should be available sometime in the future. And then right now for the next 10 minutes, Matt Lipinski from the Fort Worth District and myself are going to give you all an example application of gridded storm optimization. So an example of a study that you can use using the new storm optimization tools in HMS. So the case study that we're going to be talking about is the Upper Trinity River Silver Jackets Storm Shifting Project. Matt Lipinski was the team lead of this project, so he's going to give you a general project overview and then share results from the study and how those results are planned to be used. And then I'm going to talk a little bit about the gridded storm optimization workflow and the steps that you would need to take to reproduce this study. So this study actually started a couple years ago before these new shifting tools were available. So we had to kind of put together a scripting framework in order to be able to transpose the storms. But now, as I said, this study can completely be done in HMS, achieving the same results and done much quicker. So with that overview, I'll go ahead and pass it off to Matt.
Perfect. Can you hear me, Josh?
Yes.
Outstanding. So hello, everyone. I just wanted to take a minute, as Josh mentioned, to kind of introduce this kind of case study we're looking at here. This was a $100,000 Silver Jackets project. So with that, team members included the Corps of Engineers, Fort Worth District, the FEMA Region 6, Texas General Land Office, the North Central Texas Council of Governments, and Dallas County. And we did this also in coordination with partners from Dallas County Utility and Reclamation District, City of Irving, and Town of Highland Park. So you can see kind of a very truly collaborative effort. So through this collaboration, we were able to identify several locations along the Upper Trinity watershed as areas of interest, where we wanted to go ahead and optimize those peak discharges when shifting the storms. So we presented a list of regional historic storms to this group, and we ultimately selected 5 different larger level events that range anywhere from about a 100-year precipitation event based on Atlas 14, 24-hour precip, all the way up to well above a 500-year type event. So we tried to go kind of the full range. And what we saw was pretty interesting. And so if you go to the next slide, you can kind of see an example here. And I know this is a difficult graphic to read, but on the right, you can see an example of the FEMA 100-year floodplain in red, the FEMA 500-year floodplain, or 0.2% annual exceedance chance probability event in yellow. And then what we did is these different scenarios we ran for this one particular storm was a 200-year event as far as precip goes. Well, when we look at that, the shifting of that storm, it provided some very interesting results. Just to get more specific, we also took into account different loss parameters, things like that, to account for maybe a dry, a wet, and a best estimate scenario. And so that's what you're seeing with those 3 different floodplains, the blue and the gray and then the purple. And so this is helping us to kind of understand and provide more, going back to the FFRD discussion, things like that, more pieces of information, more tools in our toolbox to essentially ultimately reduce that uncertainty related to flood risk and help then communities become more resilient. So that's kind of that first bullet. Provide that real world type event versus just a hypothetical modeling scenario. It's something that's informative, relatable, and ultimately non-regulatory that communities are able to use and to help them better understand and mitigate flooding. That already with these local communities, we're seeing it's a valuable planning and design tool for them to ultimately become more resilient. So in the case of this Dallas County study, the communities have already started exploring this data and have intentions to use it for local emergency management actions, for future hazard mitigation planning. We've coordinated this with FEMA and others for, again, potential future use for a lot of different efforts they've got going on. The data itself, if you're interested in reviewing it in more detail, there's a published report fact sheet available at the link there on the screen. And like I mentioned, this is just helping us to overall understand this capability, but also use it as another tool in our toolbox. And so with that, I just wanted to say we've got some other efforts we're exploring across the district that are continuing to enhance and expand the use of this capability. And then we also have a Texas storm study effort that's underway to help communities and help us to identify what are the storms regionally that make the most sense to shift. And then how does that help us moving forward in terms of an inventory or data, a list of storms that we could then help communities utilize in their local efforts. Josh?
All right, thanks, Matt. So just gonna kind of quickly highlight some of the workflow, the steps that we took in the Silver Jackets project to achieve the final hydrologic results. So obviously it's very important when doing a study like this to have a good gridded precipitation data. And so for a few of the storms, we ended up using pre-processed data from the West Gulf River Forecasting Center. And then for the remaining few storms, we ended up using AORC data, which I believe is analysis of period of record for calibration data. We had good luck using that data set in this study and then also a few other studies that I've been involved in. There's a link here. I won't take the time to take you to it, but it has a nice summary table of all of the, or some commonly used gridded precipitation data sources that you might consider using in some of your studies. So really the meat and potatoes, though, of this analysis was here in this script 1 box, and this was the optimization script that we ended up using. So the main gist of it is that the vortex transposer was used to move the storm from its observed location to a new transposed location. HMS was open. A simulation run was executed with the storm in the new transposed location. The peak flow value at a downstream gauge of interest was plucked, and then the whole process repeated within an optimization routine. And at the end, what that spit out was an optimal XY storm center location that led to the maximum peak flow value at a junction downstream. And so again, the great thing is that the same sort of analysis now can be done completely in HMS without having to worry about setting up any sort of scripts. But if you were interested in how to use HMS headlessly in a scripting environment, have a link here for a tutorial that'll guide you through that process. So in this graphic here, we have the total accumulated depth raster for the tropical storm bill. And this observed storm center, I manually just kind of picked this. As you can see here, we have kind of 3 little pockets or 3 clusters. And so I just decided to pick or to specify the storm center being kind of in the middle of those clusters. But when actually running this same data set in HMS using the new storm center calculation tool, it computed it a little bit differently because it's based strictly on the cell that has the maximum accumulated value over the duration of the storm, which was just a little bit to the south of where I specified the storm center. The results are the same because the translations are all relative. But if for whatever reason you did want to exactly choose where you wanted the storm center to be, you can, as Tom mentioned, override the computed value in HMS. One other thing I just wanted to mention is that it is important, I think, to kind of clip down the domain of your gridded precipitation, but you also want to be careful to leave it large enough so that when you shift it around your basin, that the basin is always fully covered with precipitation data. So in other words, the storm center here, if it was moved to the upper left portion of the watershed, you would want the lower right to be covered as well. All right, so this graphic here shows sort of the final result of an optimization routine that was done in the Silver Jacket study, and I actually have this in HTML format, so I'll pull that up here. And so again, this is using Tropical Storm Bill. And so all of these points that you see, these colored circles, represent storm center locations that occurred during the optimization routine. And for this specific routine, the goal was to maximize peak flow at this Elm Fork junction just downstream of Grapevine and Louisville. And so the results here kind of make sense, right? So if you click on one of these green nodes up here, when the storm center was located in this area, it led to a peak flow of about 26,000 CFS at this downstream junction. So the reservoirs were able to absorb a lot of that runoff. But then when the storm centers were roughly located below the reservoirs, the resulting runoff was much higher. In this case, the optimized peak flow was about 52,000 CFS. So just kind of a really nice, cool result that summarizes the optimization routine, lets you know how sensitive a junction is to storm location, as Greg mentioned. And I wanted to mention, so this heat map capability isn't currently in HMS, but we did just get funding from the GI program to add this sort of visual result capability. So look for that to be coming here in the next fiscal year. All right, and then again, just wanted to completely or to mention that Lauren actually did the replication and validation of this study. So she took the same model and all the same grid precipitation data, used the new tools in HMS, and was basically able to exactly replicate the results from the Silver Jacket study that Matt and I are showing you. And so the big advantage here being the streamlining of the process, right? Not having to mess with any scripts. Everything's right there for you in HMS. It's well documented. And then the total runtime was significantly quicker using the new tools in HMS. So for one optimization routine, when Lauren was running them on her computer, took roughly about 10 minutes. And when I was doing kind of the same routine using the scripts, it took me well over 2 hours to achieve the exact same results. All right, just wanted to give a quick shout out to the USACE GI program, the General Investigations Program. So the tools that Tom and Lauren showed you all, that was funded by the GI program. And as I mentioned, we have additional funding this FY to kind of improve some of the visualization features that go along with storm transposition. And then also wanted to thank the Future of Flood Risk Data Program that's funding a lot of the cool SST features that Greg talked about during his portion of the discussion. And last but not least, just a couple of links. The top link will take you to our HMS homepage. So if you wanted to test out these new tools, you can download the latest 4.11 beta version of HMS. And that's also where you can access training material that Lauren put together, some tutorials and guides that will show you how to use the new tools. And then the bottom link, if you're not already a part of our email list, you can go there and subscribe. And then every time that we release a new version of HMS with new features, you'll get an email notification about that. So I think we have about 10 minutes left for questions. I will go ahead and pass this off to Chandra.
Thank you, Josh. I did see a lot of questions coming in the chat box, and they were replied already. Maybe I wanted to give maybe a few more minutes here. If there are some questions they were not answered or needed more information for those questions, maybe we could do that while we are talking about it. It's good to see that the headquarter-funded GI investigation work effort is really being helpful here. So thank you, Tom and the team, for making this work well and for greater interest and greater good. So thank you so much for doing that. And if there are any other questions, please go ahead and include in the chat box. As usual, the presentation file will be put it on SharePoint site. Along with, we will have the recorded version of this presentation would also be on the H&H COP SharePoint site. And normally we do provide the PDH certificate in the folder, as well as the list of participants or list of attendees is given in that folder also. So with that, any Tom and Greg, any last minute words of this presentation or related with in near future?
Well, I wanted to address there are thematically speaking a number of questions related to transposition domain and some of that, especially for the SAT stuff. And I don't want to take too much time, but the biggest part about a transposition domain is that that is where your fundamental assumption goes in. That box that you draw around your watershed that you're willing to move stuff around in definitely requires input of somebody with meteorological expertise on getting that drawn so that you feel confident about when taking a storm that occurred in one place and moving it somewhere else. Now you can relax that assumption a little bit with something called enhanced transposition, and Tom alluded to this with the bias grid. So basically, if you normalize that storm where it occurred, move it to its new location and undo the normalization, and you use something that describes the variability of the intensity of rainfall in that domain, it does help relax that assumption a little bit. And that's been used in a number of places that have things like strong coastal influences or orographic effects on some of that. So that's really kind of the key is developing that domain. We're doing a couple of pilot studies. One of them is for the Kanawha Basin in West Virginia, and that's a pretty big basin. That's a 12,000 square miles, and it's got pretty profound orographic influence. And so the transposition domain that we've been working on developing for that has to account for a number of different types of meteorology there. There's orographically influenced rainfall in the mountains, there's tropical storm events, there's strong convective activity over the valleys, and so the domain has to consider what area, that collection of storms and that proportion of storms could occur in. And so, again, consult your local friendly meteorologist. They love to talk about this stuff and really dig in on it. And so we're engaging with that meteorological community as much as we can. There was another question a little bit about data. Right now, the AORC, this does not constitute an official endorsement, by the way, but the AORC data set out of the National Weather Service has been our workhorse lately. It's good resolution. It's 4-kilometer data hourly, consistently available back to 1979. And it's a multi-sensor product that's been doing a pretty good job for a lot of our applications. I had a plug for the HMS webpage with other data sources on there. There are other gridded sources out there, depending on the size of your basin and how much willingness you have to download very large quantities of data. You can also start using more high resolution data sets like MRMS. Now the trick on that is the period of record is much shorter. So while you're trading, you're getting resolution down to say 1 kilometer resolution. The period of record on that is much shorter. So if you're concerned about space for time substitution, that might not be the kind of swap that you want to make. But yeah, the emphasis is on long record gridded data sets with sub-daily time steps. That's going to be the recipe for success on some of that stuff. So Tom, I'll shut up and let you say anything if you have to.
Yeah, I don't have a ton to add. I really appreciate the audience engagement today. We've had a lot of really good questions in the chat, and hopefully we've been able to track and answer those. If you don't feel like your question was answered or answered appropriately, always feel free to reach out, offline. We answer our emails and we check them. So feel free to reach out to us. We're excited about this new capability. This is the initial rollout, so we only see it growing from here. We like to get to what we call minimum viable product, and that's what this is. And we really now want to start applying these features in actual studies and applications and let that drive the innovation in our software. So what we learned from studies like the Upper Trinity study, from FFRD, those kinds of things will help us improve and enhance the software. I think there's a lot to go on right now to get you all started. And so by all means, please start using the features. They're out there already in the 4.11 betas. So go ahead and start using them and playing with them. Reach out if you have questions as you go through it.
Thank you, Tom. So before leaving, just one point I wanted to make, and that was brought out in FFRD. That's a future of flood risk data. And we're going to have more presentation on that, a detailed presentation in January to be presented by Will Lehman. And so we're going to have the presentation in January. So just wanted everyone to be aware of. So as it was brought out just in one couple of slides here. So just wanted everyone to know about that. So thank you so much for joining. We have almost at the close at the top of the hour. And thank you for joining today's webinar. And we look forward to see you again in November and December as well. So thank you and have a great afternoon. And with that, headquarters signing off. Thank you.
Thank you.
Thank you.
Thanks.